Hello everyone. Today we are presenting our project synthesizing stereo 360-degree images. This is a team project proposed by An and Shiqing from the Department of Information Sciences and Technology at George Mason University. Our project is about enhancing user experience of 360-degree images. So here we will talk about the definition of 360-degree images. A 360-degree image is a panoramic image that surrounds the original point from which the shot was taken. Users can usually view this kind of images inside a head-mounted display, and they are allowed to switch their viewing directions of the panoramic contents by moving the HMD around. Currently, the 360-degree videos are supported in major video websites such as YouTube, Meta, or Vimeo, so we can see they are becoming more and more popular. And also, this technology is a great advancement in providing immersive multimedia experience to users. Although the 360-degree image is an advancement towards immersive multimedia experience, it is still not the real immersive multimedia experience. So here we will talk about what truly defines the immersive multimedia experience. Specifically, real immersive multimedia experience allows users to perceive the depth information of all the 3D objects in the virtual environment. And to achieve this goal, users are provided with stereo images. And specifically, stereo images are those images which contains two slightly offset images, separately shown to each eye of the user, as shown in the figure below. We can see there are the two cubes inside the images are not quite the same, and on the left side, the left subfigure is shown to the left eye of the user, and the right figure is shown to the right eye of the user, and in the perspective of the user's view, the users can see and feel the offset of this cube object, and the users can feel that this object actually comes in 3D rather than a 2D picture. And here is a situation of the current 360-degree images. So currently 360-degree images are recorded by only one camera. Therefore, it contains only one panoramic image, and this same image is rendered to both eyes of the users. Therefore, it is not a stereo image, and as a result, the users cannot perceive any depth information from the image. In another word, the users will feel like they are surrounded by a 2D panoramic picture, but they will not feel they are immersed in the 3D virtual scene. Here are some solutions for this limitation. One way is to stop the monocular 360-degree image recording and start stereo 360-degree image recording from now on. Specifically, instead of using one panoramic camera to record the image, we start using two panoramic cameras placed aside each other and start recording the image at the same time. So in this way, a pair of offset 360-degree images can be generated, and once this pair of images are displayed to each eye of the user, the depth information is perceived and the real 3D immersive multimedia experience is provided to the user. However, this method will double the equipment cost to record a 360-degree image, because it requires two cameras, And also, this solution does not truly solve the problem because all the existing 360-degree images are still monocular. So a great part of those experiences are still poor for the user. In order to enhance the user experience in the huge amount of the already published 360-degree images, another solution is proposed. This solution aims to convert the monocular images into stereo ones with the assistance of machine learning technologies. Ren and Lee's team designed a deep neural network to first predict depth information in one image, and then with some handmade algorithm, the other offset image can be generated with this predicted depth information. And when this pair of offset images are rendered to each eye of the user, the stereo images is finally generated and delivered to the user. However, the network proposed in the related work cannot be directly applied to our case, because their network was designed for regular images, while in our case we have 360-degree images. And in order to feed a 360-degree images to the neural network, we first need to convert the image into an equirectangular image, as shown in the figure below. And we can see in the figure, in this equirectangular form, all the objects inside the picture are distorted to some extent. Therefore, if they are directly fed to the neural network, the predicted depth information will not be accurate, and then the further synthesized stereo images will also not be accurate. Therefore, the user experience of this kind of enhanced stereo images won't be promising. Inspired by the previous work, in this study we propose to take a step further. We aim to design a deep neural network to create stereoscopic 360-degree images from monocular ones. So a monocular 360-degree image is directly enhanced into a stereo one. And this solution does not need two cameras for the image recording, so the equipment cost is minimized. And most importantly, using this technique, all existing monocular 360-degree images can be enhanced into stereo images. So all users can enjoy real immersive multimedia experience.
So there are several of related works that have been focused on creating the depth information from stereoscopic images. For example, here we have Gard et al. And Goddard et al. Both of them propose a module called differential transformation. So the idea is that from an image, an input stereoscopic image, for example, image on the left or on the right, they input to a DCNN to create a depth map, and then they use the depth map and input to the differential transformation to create an image on the right. So overall, the idea is they can generate the other stereoscopic image in the pair. However, because they introduce this unsupervised handcraft differential transformation, typically the quality of the generated image will not be as good as a dedicated DCNN model that can generate a stereoscopic image right from the start. So here is the overall architecture of our proposed GAN, DCN, and GAN, and how we train it. Our model will consist of two main components, a generator and a discriminator. So the generator will receive an image, and the output is a synthetic image, which is the other image in the stereoscopic pair. And the synthetic image and the genuine image will be put into a discriminator. The job of the discriminator will try to distinguishing between these two images. Based on this setup, the generator will try its best to create a synthetic image that match the ground truth, and the discriminator will try their best to distinguish between the true and the fake, and this process in the end will improve the image quality of the generator. We decided to use a GAN because GAN can learn the underlying distribution of the mapping from the left to the right of the stereoscopic image pairs. Next, we discuss on how to generate the dataset to train our model. We will use videos, stereoscopic 360-degree videos from YouTube. In this platform, we observe that there are various videos captured by stereoscopic cameras, and we have been able to download a few of them to verify that. Our goal would be to collect enough dataset to train our model. So initially we will set our goal is to collect at least 40 videos. Then the video will be processed following this pipeline. First, we will select manually several frames from the video such as the content would be diverse enough. Then we will separate the left and the right image for each frame to create the ground truth for the training. Then we will rescale the image frame into smaller size, even though the desired size of the frame should be in 4K or 2K, but for the limitation of the computation power of deep learning, probably we will keep the resolution as around 500, but it would be depends on the actual implementation of the model. For evaluation, our biggest concern would be the impact of the synthetic image to the user experience. Specifically, we are concerned that a video could cause some negative effects such as dizzy and nausea to user, which is not good. However, we will not directly evaluate those specific measures because they are quite hard and expensive, which usually involve with many recruits and come up with a reliable metric for such a effect. Instead, in this project, we will use video quality evaluation, and the two most popular metric we will use is the SSIM and the PSNR. In particular, we will compare the synthetic image with the ground truth image, and the differences will be shown in SSIM and PSNR value. To benchmark the performance of our model, we will compare the image generated from our model with image generated from most recent work is the work from Goddard et al. So in this project, we present the need to create the depth experience for monoscopic 360-degree videos, which is quite popular on the internet nowadays. And then we propose a new model that uses the generative architecture to synthesize the stereoscopic image or frame from monoscopic counterpart. And finally, we present our approach to train and evaluate our proposed network. Finally, here is our expected timeline for our project. First task is dataset generation, should take around 2 weeks. Then we will prototype the model, make the model run, and can be trained on a small data set, which also should take around 2 weeks. And then model training and evaluation, which should take 1 week for each. And finally, report writing and presentation preparation should take the rest of the time. So not all of the tasks here have to wait for each other, but some of the tasks can be done concurrently. For example, step 1 or 2, or step 4 and 5. So we expect that it should be doable for our given time for the rest of this semester. So that's conclude our presentation for our project proposal. And here are the two major references that we use for this project. And thank you for listening and viewing.